Hello there, and welcome back to Sleepy Science Stories, where the night sky unfolds softly and each thought drifts at the pace of breath. Perhaps you're already lying down, wrapped in quiet, the air still around you. The lights are low. The world has slowed. Somewhere outside, the dark sky waits, holding the shapes of distant galaxies. Tonight, we'll wander toward one of the strangest ideas in the universe, a place where gravity folds light into silence, where time stretches, bends, and nearly stops. A black hole isn't a thing in the usual sense. It's a condition of space itself, a deep curve in the fabric of reality. To be near one is to watch time behave differently, to see light hesitate to glimpse how fragile the rules of existence can be. But you don't need to solve equations now. You only need to listen. Let your mind drift like starlight drawn inward, slow and weightless. Tonight's journey. The weird physics surrounding black holes that will make you question your existence. We'll explore what they are, how they form, why they twist space, leak heat, and blur the line between matter and meaning. And as we move through each idea, remember, you don't have to stay awake. The cosmos continues even when your eyes close. If these quiet wanderings among the stars bring you calm, a soft touch on like or a whisper of subscribe helps this small corner of the cosmos find others who need a little stillness too. Breathe in, breathe out. Let your thoughts settle like dust around a quiet star. And when you're ready, we'll begin with why black holes are so very strange. Even among all the wonders of the universe, stars that live and die, galaxies that drift like slow rivers of light, black holes remain the most elusive. They do not shine. They do not reflect. They do not even occupy space in the ordinary way. They are regions where the very fabric of reality folds inward on itself, a kind of quiet implosion of geometry. To speak of a black hole is to speak of gravity taken to its limit. Gravity so dense, so absolute, that even light, the swiftest traveler in existence, cannot escape its pull. We are used to thinking of gravity as gentle, the weight that holds us to the earth, the curve that keeps planets circling the sun. But near a black hole, gravity becomes something different. It becomes a sculptor reshaping time and space into new and unfamiliar forms. Imagine space as a smooth, invisible fabric. Every object with mass planets, stars, even you presses into that fabric just a little. Now imagine a mass so concentrated that the fabric doesn't merely dent. It plunges downward, forming a well so deep that the bottom never quite ends. That is what a black hole is, not an object sitting in space, but space itself bent so far that down ceases to have meaning. From far away, a black hole looks simple, a shadow surrounded by light. But beneath that simplicity hides one of the most complicated structures ever conceived. Near its boundary, time stretches thin. A second close to the edge can become years or centuries for someone watching from far away. Even light that grazes its rim is bent into orbit so tight that it can circle many times before escaping. The black hole is not just strange. It is a mirror that shows how incomplete our intuition really is. Einstein's general theory of relativity predicted their existence long before anyone believed they were real. His equation suggested that if enough matter collapsed into a small enough region, space-time itself would curve without limit, forming what we now call a singularity. a place where the mathematics diverge, where the known laws of physics lose their language. Even Einstein was uneasy about that possibility. He thought nature would somehow avoid such extremes. But nature, as it turns out, is less concerned with comfort than with possibility. As telescopes and theory advanced, astronomers began to realize that the cosmos is filled with these dark wells. They are not rare. They sit at the hearts of galaxies, including our own Milky Way. They hide in the remnants of massive stars. They wait in the quiet between the stars, invisible but immense. Everywhere we look, gravity seems to remember how to fold itself this way. Black holes are weird, not just because they consume, but because they define boundaries we cannot cross, not physically, not conceptually. The event horizon, that invisible edge, marks a line where our understanding stops. Inside, every path forward leads inward. Every timeline ends at the singularity. There is no stable orbit, no escape route, no signal that returns. It is not a surface in the ordinary sense. It is the edge of knowability itself. And yet, what lies just outside is equally strange. If you hovered near a black hole, somehow resisting the pull, you would see the universe behave as if trapped in slow motion. Distant clocks would seem to race while your own heartbeat fell behind. Colors would shift toward red light, stretching as time itself stretched. For an observer far away, your descent toward the event horizon would appear to slow, then freeze your image, dimming and fading as if time refused to let you finish falling. In this way, a black hole becomes not just a place, but a performance of time. It shows us that time is not universal. It bends, flexes, and even stops depending on where you are. Near a black hole, seconds and centuries can occupy the same moment. This is one of the reasons scientists call them relativistic laboratories. They reveal relativity not as a theory, but as a lived experience of the universe. And there is something paradoxical about their simplicity. A black hole can be described completely by just three numbers: its mass, its spin, and its electric charge. That's all. No surface features, no scars from its formation, no record of what fell in. Everything else, composition, history, identity, is erased. This idea is known as the no-hair theorem. It means that a black hole is the ultimate simplifier. No matter how complex the matter that created it, what remains is perfectly featureless, smooth, silent, identical to any other with the same three values. To contemplate that is unsettling. It suggests that even individuality, the intricate detail of stars, atoms, and patterns, can be swallowed by symmetry. It invites the question, if all information is lost, what happens to the past? Is the universe allowed to forget? These questions lead directly into one of modern physics' greatest mysteries, the information paradox, which challenges whether quantum mechanics can coexist with Einstein's geometry. For now, we simply observe what we can, and what we see defies expectation. At the center of our galaxy, the black hole called Sagittarius A sits in stillness. Yet every few minutes, it flickers faintly, as if light itself is negotiating the right to leave. Around distant galaxies, we see jets of radiation shooting out across millions of light years, powered not by explosions, but by gravity alone. energy drawn from rotation and friction from matter spiraling inward faster and faster until it glows white-hot. This energy comes not from what the black hole contains, but from what it forbids. From the struggle of falling matter to resist falling forever. It helps to remember that black holes are not black in the absolute sense. Their edges are illuminated by what they consume. Gas dust, even entire stars, form swirling disks of light around them, their energy released in the final seconds before disappearance. So, while the heart of a black hole is silent, its surroundings are among the brightest objects in the universe. They remind us that even destruction can be luminous. And still, black holes remain strange on a deeper level. Because when we talk about them, we are forced to let go of normal categories inside and outside, before and after cause and effect. In the curved space near a singularity, paths fold back on themselves. Events can swap their order. Time can close into loops. And though these are mathematical possibilities, rather than physical ones we can test, they whisper of a universe that might not be linear at all. You could think of a black hole as the ultimate boundary between knowing and mystery. But you could also think of it as a doorway, a transition from one way of being to another. Not necessarily a tunnel to somewhere else, but a reminder that even reality has horizons, and beyond them perhaps new forms of existence we can't yet imagine. Some physicists have described black holes as the atoms of space-time, the fundamental units of gravity itself. That idea captures their essence beautifully. Each one is a place where the smoothness of the cosmos breaks into quantum grain, where curvature becomes energy, where being becomes question. So when you think about black holes, about these invisible hearts of galaxies, about gravity so strong it reshapes time itself, you're really thinking about the edges of what it means to exist. They are not monsters devouring everything, but teachers reminding us that even the laws of nature can be strange, and that the universe in its quietest moments is still experimenting with possibility. Let your mind linger there for a moment in the thought of a place where light can orbit forever, where seconds stretch into infinity, where the simplest equation hides the deepest truth. Because this is only the beginning. Every black hole begins somewhere too, not from nothing, but from a star that once burned balanced, and finally fell inward. Every black hole begins as light, as heat, as a star that once burned so fiercely it held itself against collapse. In the quiet cycles of the cosmos, even balance has a lifespan. For a long while, a massive star lives in perfect symmetry, gravity, pulling inward, fusion, pushing outward. It is a dialogue written in plasma, a long, slow argument between weight and fire. The inward pull wants to shrink the star into nothing. The outward pressure born from nuclear fusion wants to keep it open, radiant, and alive. Inside that radiant shell, atoms collide at unimaginable speeds. Hydrogen becomes helium, helium becomes carbon, and so the star builds the ingredients of life while fighting its own gravity. Every flicker of light from its surface is a whisper of that struggle. Every photon released is a note from a furnace refusing to fall inward. But nothing lasts forever, not even equilibrium. Over millions of years, the star changes. Its core grows heavier, its energy thinner. The elements inside climb the periodic ladder: carbon, oxygen, silicon, iron. each step producing less light than the one before, until it reaches iron, and that for a star is a dead end. Iron does not give energy when fused. It takes energy away. When a core fills with iron, fusion falters. The outward breath stops, and the star which has spent eons resisting gravity finally exhales for the last time. Then gravity wins. In less than a heartbeat, the core collapses. A sphere the size of a sun shrinks to the size of a city. Atoms break apart. Protons and electrons fuse into neutrons. The collapse is so violent that the outer layers rebound a detonation so vast it can outshine an entire galaxy for weeks. That explosion is called a supernova, the last brightest moment of a dying star. What remains depends on mass on how much gravity is left in the ashes. If the core is small enough, it becomes a neutron star, a sphere of ultra-dense matter so compact that a teaspoon of it would weigh a mountain. But if the mass crosses a certain limit about 3 times, the sun's even neutron pressure cannot resist the pull. The collapse continues. Gravity overwhelms everything, even light itself. The star's identity vanishes. Space-time caves inward, and a black hole is born. It happens quietly, a transformation so complete that no trace of the original structure remains. In moments, a star's history, the atoms, the light, the music of its nuclear heart is folded into silence. But the silence itself still has gravity, still shapes the world around it, still whispers its presence through motion, through heat, through distortion. When we say the death of a star, it might sound like an ending, but in the cosmic rhythm, it is more like a change of tempo. The light fades, but the curvature remains. Matter gives way to geometry. Energy becomes the shape of space itself. And so, from one kind of being, another begins. In this way, black holes are not born from destruction, but from transformation. They are continuity through collapse, a new form of existence that inherits mass without form. When we look at the night sky, every supernova, every flickering remnant might be a future black hole waiting to cool into invisibility. Yet there are other paths to black hole birth, stranger, quieter ways that take place not in the life of one star, but in the meeting of many. In dense clusters, stars sometimes merge. 2 heavy stars collide, their combined mass pushing them over the threshold. In the young universe, when everything was closer and hotter, such mergers may have been common. Some black holes might have formed not from death, but from union 2 lives collapsing into one deeper shadow. There is also the possibility of primordial black holes born not from stars at all, but from density fluctuations in the first moments after the Big Bang. If certain regions were slightly denser than others, gravity could have crushed them before stars even existed. Tiny black holes, smaller than mountains, might have flickered into being in the first fractions of a second after creation. If they still exist, they drift invisibly through space, evaporating so slowly that the process would take longer than the age of the universe. Some may already have vanished, leaving behind only radiation, a faint final sigh of their existence. Others may still wander unseen, the smallest possible echoes of the universe's earliest heartbeat. And then there are the giants, the ones that live at the centers of galaxies. Supermassive black holes, millions or billions of solar masses, so vast that entire star systems could orbit inside their gravitational reach. How they formed is one of astronomy's lingering mysteries. Perhaps they grew slowly, feeding on gas and stars over billions of years. Perhaps they started big, seeded by the collapse of the first supermassive stars. Or perhaps they were born directly from clouds of pure hydrogen, collapsing under their own weight, bypassing the stage of stars entirely. However they came to be, they now rule the cores of galaxies like silent anchors. Their presence shapes the dance of stars, the motion of dust, the rhythm of cosmic evolution itself. Without them, galaxies might not hold together. They are the dark hearts that keep the spirals turning. Every type of black hole, stellar, supermassive, or imagined and intermediate, shares one thing: an origin in imbalance. Something tips too far toward gravity, and the result is a place where time cannot escape. And yet their creation is not an act of violence in the moral sense. It's the natural consequence of physics following its own rules. A star collapses because that is what gravity does when nothing stands against it. In that surrender, there is no chaos, only inevitability. If you could watch it happen safely, you might not see much at all. As the collapsing core shrinks, the light slows and reddens. From far away, the process looks as though it never finishes. The star seems to freeze at the edge of the event horizon, fading gradually from visibility. To an outside observer, the formation of a black hole is infinitely slow. But from the star's own perspective, it's over in an instant. Two views of the same event, both true in their own frames of time. That paradox, simultaneous motion and stillness, is part of what makes black holes so strange. They exist at the intersection of perspectives. For those who fall in, time continues. For those who watch from afar, time halts. In that difference lies the essence of relativity itself. And so every black hole is a kind of cosmic memory recording the universe's extremes. It remembers the density of stars, the geometry of space, the stretch and flow of time. It is an archive of what matter can become when no other law remains. You might think of one forming somewhere right now, a massive star in a distant galaxy collapsing inward, its final light racing outward across millions of light years while its core falls forever inward. That light may reach us long after the star has vanished. We see its death as if it were still alive, because in the language of space-time, the past and present coexist across distance. And so the creation of a black hole is not merely an ending, but a reminder that the universe holds memory and light. Every photon carries a message from something that was. Every wave of radiation tells us what used to be true. Even when a star dies, its light continues traveling through ages, illuminating the moment long after it is gone. The birth of a black hole marks a threshold. On one side, matter, fusion, radiation. On the other, pure curvature, an inward silence that contains everything it once was. And somewhere between those two lies time itself, stretching, slowing, bending until meaning dissolves into geometry. Black holes are weird, yes, but their formation is simply the cosmos doing what it always does, transforming form into pattern, substance into motion, and motion into stillness. From that stillness, everything else unfolds. The bending of light, the distortion of time, the flicker of distant X-rays, all of it traces back to this act of falling inward, And so, as we continue this quiet journey, let your thoughts sink slowly with the star, past the surface, past the glow toward the invisible edge, where time begins to hesitate. Because at that edge, we encounter the most haunting feature of all the event horizon. The boundary where light, time, and certainty itself come to rest. The event horizon is not a surface, not a wall, not a membrane, not a place you could touch. It is a boundary written in light, a threshold between what can be known and what forever retreats. In the last part, we watched a star collapse inward, its final breath folding space, until no outward path remained. Now we linger at that invisible line, the rim where gravity becomes complete. The event horizon is the ultimate horizon, not because it hides what lies beyond, but because beyond it, beyond has no meaning. Imagine you are falling toward it. There is no impact, no jolt. Space does not resist. It stretches quietly, letting you drift deeper as if gravity were not pulling you, but space itself were flowing inward. In a sense, that's exactly what happens. Near a black hole, space doesn't just curve, it moves. It streams inward like a waterfall. The event horizon is where the inward flow reaches the speed of light. Even light, which usually outruns all motion, cannot swim against that current. To you falling, nothing unusual happens as you cross the line. The stars remain above, faint but present. The horizon does not flash or shimmer. You pass through as if through air. But to an observer far away, the view is entirely different. They see your fall, slow, your light stretched into deep red, your image fading, freezing just above the edge. You never appear to cross. You become an afterimage, a ghost of photons trapped in slow motion. This difference between what is seen and what is felt is one of the strangest consequences of relativity. Time itself depends on where you stand. Close to a massive object, clocks run slower. That's not a trick of perception. It's the structure of space-time itself. Gravity bends not only paths through space, but the flow of time along them. Every heartbeat near the event horizon echoes through centuries for the observer outside. To fall inward is to slip into slower and slower time. You could watch the future unfold above you as you descend. It is easy to imagine the event horizon as an edge, but it's better to think of it as a silence, a place where information stops being shared. Not because it vanishes, but because its signals can no longer climb out. Even light, our fastest messenger, finds its path bent back inward. So the horizon is not a thing in itself, but the last place where outward communication is still possible. It's the universe's final whisper before quiet. And yet quiet does not mean empty. Just outside that line space roars with motion. Gas and dust swirl at incredible speeds, accelerating as they approach the brink. Friction turns this falling matter into heat and light, a final blaze before disappearance. From a distance, the region around the event horizon is brighter than any star. But the horizon itself stays black, a hole in the pattern of the universe, a shadow cast by gravity. The image captured by the Event Horizon Telescope in 2019, that blurred, glowing ring around darkness, was our first glimpse of this shadow. What we saw wasn't the black hole itself, but the light orbiting close to it, circling at the very limit of stability. That ring is called the photon sphere, a razor-thin region where light can loop around the hole many times before escaping. It's not part of the horizon, but it's shaped by the same curvature. The glow we see is light bent into orbit, its path curved so severely that it nearly becomes a circle. If you could hover above this region, the view would defy imagination. Behind you, the universe. Before you, a darkness that bends even your own reflection. Every direction would lead eventually inward. Light from the same star could arrive from multiple angles, looping around the hole like a ribbon before reaching your eyes. Up and down would lose meaning. Inside and outside would blur. You would see yourself, seeing yourself, a cascade of images spiraling into infinity. This is what it means for space-time to bend, not only distance, but perception. The geometry of a black hole turns vision into recursion time, into distortion, and motion into inevitability. If you drift closer, the pull becomes stronger. Gravity increases not linearly, but exponentially. Just a little closer, and the difference in gravity between your head and your feet could stretch your body like a thread of light. Astronomers have a gentle word for this process: spaghettification. It sounds whimsical, but it describes one of the most extreme experiences imaginable. Matter doesn't merely fall, it elongates, pulled thinner than atoms, until the concept of shape itself dissolves. The same happens to light. Wavelengths stretch beyond detection information, fading into the background hum of space. But these aren't horrors to the cosmos. They are simply transitions, the way gravity completes its work. The universe doesn't resist extremes. It experiments with them. There's something deeply poetic about how time behaves near an event horizon. For the falling traveler, the end arrives swiftly. For the distant observer, the fall never completes. Two versions of reality coexist, both true, both contradictory, each written into the geometry of space-time. Perhaps in some sense, every black hole is an archive of these contradictions, the memory of all possible perspectives. And then there's the question, what happens to what crosses the line? Does it vanish? Does it persist inside, compressed beyond recognition? We don't know. Einstein's equations predict a singularity, a point of infinite density where space-time curves without bound. But infinities are signs that our theories are incomplete. Somewhere beyond the horizon, the known laws of physics break down. Quantum theory and gravity must speak together, but for now, they only whisper. It's possible that what we call a singularity is not a point at all, but a region of tangled quantum geometry where space itself is granular, where time flickers in tiny loops. Loop quantum gravity suggests that such regions could bounce, releasing energy back into the universe, slowly transforming the black hole in its final moments into something like a white hole, a place where matter flows out instead of in. If true, then even the horizon is not eternal. It too might fade, dissolving like the memory of an event once hidden beyond sight. But from where we stand now, the event horizon remains one of nature's quietest wonders, a border drawn not in matter, but in possibility. It's the point where information becomes unreachable, yet not necessarily lost. A paradox softly glowing at the edge of comprehension. Think of the photons that just barely escape spiraling outward, carrying whispers of what happened at the brink. They travel for thousands, even millions of years, until some of them reach our telescopes. When we capture their light, we are in a way catching messages from the edge of time itself. That light tells us not what's inside, but how space behaves nearby. It maps the shadow, the spin, the magnetic storms around the horizon. It reminds us that even the darkest places still communicate in their own language of distortion and delay. And perhaps that is the quiet lesson of the event horizon, that there is always a boundary between what we can know and what we can only imagine. The edge is not meant to be crossed. It's meant to be understood as part of the whole, the way silence belongs to music, the way night defines the stars. So linger here on the threshold between falling and frozen, between motion and stillness. The black hole's edge hums quietly in its own rhythm, its own tempo of time. Each second that passes here contains eternities for someone else. And from this horizon, we will soon look outward again toward the evidence we found that proved such places exist at all. The clues that first revealed their presence long before we could see their shadows directly. For a long time, black holes were theory, only a whisper in Einstein's mathematics, a thought experiment about what might happen if gravity were allowed to finish what it starts. No one had seen one. No one even believed nature could permit them. They were too strange, too final, too perfect in their silence to exist in a universe full of noise. And yet the universe does not fear strangeness. It expresses it quietly, patiently waiting for us to learn how to listen. After all, we had just spoken of the event horizon, that invisible boundary between what can be seen and what cannot. But for decades, black holes themselves lingered just beyond a similar horizon, the edge of human evidence. We could imagine them, but we could not yet prove they were real. It began as many cosmic discoveries do with light that wasn't behaving as expected. In the late 1960s, astronomers studying the sky in X-rays found a source in the constellation of Cygnus the Swan. It was brighter than anything they had seen before in that wavelength, but nothing visible appeared in its place. A bright companion star orbited an unseen partner. Something massive, something invisible was drawing matter from that star and devouring it with invisible force. The object became known as Cygnus X1. It was the first true black hole candidate, a place where gravity ruled so completely that only its influence could be observed. The falling gas glowed in X-rays as it spiraled inward, releasing its last heat before silence. The star, trapped in orbit, circled a darkness it could never escape. For the first time, we had indirect proof that black holes were not just equations. They were events happening right now in the night sky. It's strange to think that proof of the invisible came through light, through the very thing a black hole consumes. But that is the paradox of the cosmos. Even darkness can be revealed by how it shapes illumination. Cygnus X1 became a cornerstone of astrophysics. The data showed a mass too large to be a neutron star, too compact to be anything else. Einstein's reluctant monsters were real after all. And yet the discovery brought as many questions as answers. How many of them exist? How do they grow? What happens at their edges where time slows and light bends? The decades that followed were a slow unfolding of those questions. Telescopes grew stronger. Detectors became more sensitive. We learned to read not only light, but the invisible rhythms of gravity itself. By the 1990s, astronomers began to suspect that nearly every large galaxy hid a supermassive black hole at its center. At first, this was an audacious claim that something invisible millions or billions of times heavier than the Sun was quietly anchoring each galactic core. But motion tells stories even light cannot hide. Stars near the centers of galaxies moved too quickly, too precisely, as if orbiting an unseen weight. That weight could only be a black hole. In our own Milky Way, we found such a heart. A source of radio waves named Sagittarius A, nestled in the direction of the constellation Sagittarius. Over 20 years of observation revealed stars whipping around it at incredible speeds, some completing orbits in just a few years. The gravitational pull required to shape such motion meant only one thing: a black hole 4 million times the mass of our Sun sat at the galaxy's center. It does not roar or blaze. It waits. Quiet, steady like a pulse beneath the fabric of the galaxy. And yet, there are times when it stirs. Flashes of infrared light, bursts of X-rays, signs that clouds of gas are brushing too close, heating and vanishing beyond the horizon. Each flicker is a reminder that even in stillness, the center is alive. The universe offered more proof still in waves that could not be seen at all. In 2015, the LIGO Observatory detected something extraordinary: ripples in space-time itself, a faint stretching and squeezing that passed through Earth. Those waves came from two black holes colliding a billion light-years away. Each had spiraled toward the other, losing energy through gravitational waves until they merged into one larger quivering horizon. For a fraction of a second, that merger released more energy than all the stars in the observable universe combined, but not as light, as gravity's own vibration, the cosmos ringing like a bell. It was the first direct detection of gravitational waves, and with it the first confirmation that black holes not only exist, but dance, collide, and sing across the fabric of time. When LIGO detected that signal, a tiny chirp lasting less than half a second, we were in a sense hearing the universe breathe. It was as though space-time had whispered, "Yes, they are real." After that, the picture grew clearer. We found merging black holes again and again, some 10 times, some 50 times the Sun's mass. Each merger left behind a single larger black hole, spinning from the momentum of its creation. And as they merged, the event horizons briefly merged too, stretching, twisting, and then settling into new geometry. Even destruction, it seems, finds balance again. These discoveries confirmed what theory had suggested all along: that black holes shape the universe not through violence, but through structure. They hold galaxies together, seed new stars, and even influence cosmic evolution on the largest scales. And yet, for all the detection, for all the measurements and data and confirmation, a deeper mystery remained. We had never truly seen one, only its effects. only its gravity, only its echo. Until 2019, when the Event Horizon Telescope, a network of radio dishes spread across the Earth, captured that now familiar image, a golden ring surrounding a dark center. It showed the supermassive black hole at the heart of galaxy M87, 55 million light-years away. A shadow cast by something that should have no shadow. The ring we saw wasn't a circle of light from the horizon itself, but from matter orbiting just outside it, heated to billions of degrees, twisting in magnetic fields, glowing as it spiraled toward oblivion. The black center was not an object, but the absence of all return paths for light. That photograph was a threshold in human history, the first visual proof of a place where space ends its own map. To gaze upon it is to glimpse physics reaching its limit, a picture of time stretched to its breaking point. Every pixel in that image carries centuries of theory, decades of patient calibration, and the light of countless atoms sacrificed to gravity. Even so, our vision remains partial. We cannot peer beyond that shadow. We cannot yet see what happens inside. But perhaps we do not need to. The horizon is enough. It tells us that the equations were right, that the universe holds its mysteries close, but not forever hidden. Each observation, Cygnus X1 Sagittarius, A the LIGO waves. The M87 shadow is a door opening slowly into darkness, each one revealing a little more of how nature balances creation and collapse. And there's something quietly beautiful about that progression. From invisible equations to X-rays and radio signals to the tremor of space-time itself, all of it points toward the same truth that black holes are not anomalies, but part of the cosmic order. They are the punctuation marks in the language of the star's pauses, where energy rests before resuming its endless conversation. So when you think of that golden ring, or of two distant black holes merging, or of the quiet gravity at the heart of our galaxy, remember we are witnessing the universe recognize its own reflection. What once was only mathematics has become a moving, luminous reality. What once was impossible is now observable. And what once hid in silence now hums softly in the background of existence. From this evidence, new questions arise about what escapes the horizon, about the faint theoretical warmth that might leak from its edges. A phenomenon predicted by one mind that dared to wonder if even black holes might not be perfectly dark. From the edges of blackness, a whisper emerges, a murmur from where nothing should speak. After all our searching, after Cygnus X1, after LIGO, after the golden ring of M87, we believed black holes were pure silence, perfect endings to every story that fell within. But in the quiet years that followed, one voice suggested they might not be completely mute. That voice belonged to Stephen Hawking. In the 1970s, sitting beneath the weight of his own failing body, he asked a question that would change how we see the universe's most absolute places. Could even a black hole master of gravity and darkness still obey the laws of quantum physics? The rules of the smallest things? His answer was yes. And from that yes came one of the most delicate ideas in modern science, Hawking radiation. To understand it, we must remember what empty really means. We picture space as a vacuum, a silent stage where stars perform, but to quantum physics, even nothing hums. The vacuum is not empty, it seethes with fluctuations. Tiny pairs of particles and antiparticles appear for an instant, born from the energy of uncertainty itself, then vanish again, annihilating each other before they can be seen. It happens everywhere, all the time, a constant shimmer beneath the surface of existence. Now imagine that same quantum sea at the very edge of a black hole, where gravity is so extreme that even the definition of inside and outside becomes uncertain. When one of those particle pairs flickers into being near the horizon, gravity can tear them apart before they reunite. One particle falls inward, trapped forever. The other escapes. To an observer far away, that escaping particle appears as radiation, a faint glow leaking from the darkness. It is not light that escaped the hole. It is light newly born because one half of a pair was stolen. To preserve the laws of energy, the black hole itself must pay the debt. It loses a tiny bit of mass, its gravity weakening imperceptibly with each release. Thus, Hawking showed that black holes are not eternal. They slowly evaporate. They radiate heat not from their contents, but from the restless quantum fabric around their borders. The power of this idea is quiet, almost invisible. The radiation is faint beyond measure. A black hole as massive as a star would glow colder than the cosmic background itself. We cannot yet detect it. And yet the theory stands strong, woven from the mathematics that join general relativity and quantum field theory in uneasy truce. What Hawking discovered was not just a property of black holes, but a principle of balance. No horizon is absolute. Even the universe's most one-sided process, matter falling inward, is not immune to the reciprocity that defines nature. Something must return, however softly. Over unimaginable time, this radiation would shrink a black hole, making it smaller, denser, hotter. As it contracts, the process accelerates. When it becomes tiny, perhaps the size of an atom, its final evaporation would release a last burst of energy, a whisper turning briefly into a flare. Then nothing. No singularity. No shadow. Just equilibrium restored. It's almost poetic the universe does not allow even the purest darkness to last forever. Everything changes form. Even gravity's masterpiece eventually returns its borrowed energy. Physicists have tried to glimpse hints of this process. They can't create black holes in the lab, but they can mimic their behavior. In tanks of super-cooled atoms in streams of light moving through special materials, scientists have built analogs. Tiny systems where waves behave as if trapped behind an artificial horizon. And in those experiments, faint radiation appears a thermal signal eerily similar to Hawking's prediction. These sound black holes or sonic horizons are whispers of agreement between theory and nature. It's a humbling thought that the same mathematics governing stars and galaxies can also describe ripples in a laboratory tank. That the cosmos at every scale follows the same rhythm of exchange energy, borrowed energy returned. But Hawking radiation raised another question, one deeper still. If a black hole slowly evaporates, what happens to the information it once held? When matter falls in its physical properties, temperature, composition, even identity seem to vanish. If the whole later radiates away as featureless heat, then information appears lost forever. But in quantum physics, true loss is forbidden. Every process, no matter how chaotic, must in principle be reversible. So where does that information go? This is known as the information paradox, a riddle that has haunted physics for decades. Some believe the information is encoded in the radiation itself, subtly imprinted on the escaping particles like a code within heat. Others think it might remain on the event horizon spread across it like a hologram, a two-dimensional record of everything that ever crossed. This holographic principle suggests that our universe, too, might be a projection from some deeper surface. A strange idea, but one that seems to echo the patterns of physics again and again. If true, then black holes are not destroyers of information, but keepers of it. Their horizons may hold the compressed memory of everything they consume, a cosmic library written in invisible light. The beauty of Hawking's idea lies in its balance between contradiction and harmony. Gravity, the grand continuous curve of space-time and quantum mechanics. The grainy dance of particles are usually at odds, but in the trembling border near a black hole, they meet. They speak a common language for just long enough to remind us that reality itself is one thing viewed through different eyes. In that meeting, something almost spiritual occurs. The black hole, once thought to be an end point, becomes part of a larger cycle. Absorption gives way to emission. Silence gives way to faint music. The dark learns how to shine again. Hawking radiation is gentle, so soft that the universe hardly notices. A stellar mass black hole would take 1067 years to evaporate, a number far beyond comprehension. By then, galaxies will have dimmed stars, will have burned to embers, and the cosmos will be a sea of cooling atoms. In that far future, black holes will be among the last voices left, slowly releasing their stored energy into the silence of space. Perhaps that is the final act of the universe's long story. Everything that once fell inward will drift outward again as faint heat filling space with one last warmth before all becomes equal and still. There's a calm symmetry in this thought. Even black holes, the most absolute expressions of gravity, participate in the universal balance between creation and decay. They are not eternal prisons. They are part of the breathing of the cosmos, inhale and exhale, collapse and release darkness and light. The paradoxes they generate about information, about time, about loss are not signs of failure, but hints that our understanding remains unfinished. Somewhere beyond our current mathematics, gravity and quantum fields must reconcile completely. And when they do, perhaps the horizon will no longer seem like an ending, but a fold, a turning of one page to another. So as we drift in thought near that quiet edge, imagine a black hole, not as a hole at all, but as a slow transformation of matter into meaning. A place where light learns to pause, and where even silence radiates gently into forever. From here, our journey can move outward again to what space itself does in response to a spinning hole, how the very fabric of the cosmos twists, pulling time and direction into spirals around that darkness. The thought of Hawking radiation lingers, a reminder that even silence glows faintly, that even the darkest boundaries hum with hidden balance. From that slow leak of light, a larger question begins to take shape. If black holes are not things but curvatures, transformations of space itself, then what is anything? What is matter if it can vanish into geometry and return as heat? Einstein once said that matter tells space how to curve and space tells matter how to move. A simple sentence, yet beneath its calm logic lies a profound possibility that everything we call real is an echo of curvature, a shadow cast by the bending of the invisible. We are used to thinking of space as emptiness, a stage on which the universe performs, but relativity changed that view. It showed that space and time are not background. They are participants, flexible and alive, shifting in response to energy and motion. Gravity is not a force that pulls across distance, but a warping of the stage itself. Planets move along those curves, not because they are tugged, but because the floor beneath them is sloped. Black holes take this principle to its limit. They are not objects in space-time, they are places of space-time. The shape itself becomes so steep, so deep, that inside and outside lose distinction. A black hole is where space-time forgets how to remain flat. It folds into itself like fabric drawn to a single point. And if matter is merely energy following these curves, then perhaps what we call substance is nothing more than geometry repeating. Mass and space are two ways of describing the same pattern. One speaks the language of motion, the other the language of shape. It's a difficult idea to hold in the mind that we might be made not of solid particles, but of relationships between curvatures, temporary eddies in the flow of the universe. You, me, every atom. Each a brief arrangement in the endless flexing of reality. In that sense, black holes are not alien. They are us taken to an extreme. The same mathematics that describes your weight, your breath, your orbit around the sun also describes the horizon around a singularity. Only the degree differs. We are all in some small measure the bending of the same invisible sheet. It's a quiet, humbling thought that the universe might not contain things but processes. Not nouns, but verbs. That existence itself is a continuous unfolding a choreography between energy and form. In this dance, black holes are moments of perfect tension. They are where the curvature folds inward so deeply that the normal rhythm of cause and effect briefly loses its beat. Inside time and space swap roles. Distance behaves like duration, and duration becomes a kind of distance. The equations still hold, but their meanings trade places as if the universe were playing its own inversion, a musical phrase turned upside down. Even light obeys the new tempo. Instead of traveling through space, space itself carries light inward. Instead of the future moving away from the past, they twist around each other inseparable like two strands of the same cosmic DNA. When we think of black holes this way, the border between physics and philosophy softens. We begin to wonder not only how the universe behaves, but what being means within it. If matter is a curvature and curvature a way of encoding energy, then perhaps consciousness too is a temporary pattern, a local harmony within the greater song of space-time. And if that's true, then existence is not about permanence, but about participation. To exist is to curve to influence, to shape and be shaped. Even thought, even emotion are gentle ripples in the same field that holds stars and galaxies. This idea matter as a shadow of geometry was not invented for poetry, though it carries a poet's resonance. It grows directly from Einstein's equations and from the newer frameworks of quantum gravity that followed. In some of these models, particles are viewed as tiny loops or vibrations of space itself, knots in the fabric of existence. Their mass is not intrinsic. It arises from the energy of curvature. In other words, a proton is not a pebble in space, It is space momentarily folded into a stable whirlpool. So when a black hole forms when matter collapses and curves beyond recovery, it is not that the matter falls into space-time, it becomes space-time. It transforms from a localized swirl into a vast indentation in the universal sheet. The material and the geometric are not separate categories. They are different expressions of the same underlying entity. To look at a black hole, then, is to see space thinking about itself. A pure feedback loop energy folding inward until the only thing left is the pattern of the folding itself. It is self-reference made cosmic. That realization reshapes how we think about reality. Perhaps the universe doesn't contain information. Perhaps it is information woven into the geometry of its own fabric. Every field, every particle, every movement of energy is a computation carried out in space's curvature, a self-similar endless calculation of how to balance energy and symmetry. And yet, amid these abstract ideas, a human truth remains. You are part of that same geometry. The atoms in your body, the iron in your blood once drifted in the heart of a star, then fell through the gentle pull of gravity, perhaps even near a black hole. Your existence is proof that the universe's curvature can think, can wonder, can listen to itself. Perhaps that is why we find black holes so mesmerizing. They are mirrors for our own search for understanding. They remind us that to observe something is also to become part of its story, because observation itself bends the field of possibility. When you gaze into the idea of a black hole, its horizons, its paradoxes, its endless gravity, you are really gazing into the rules that allow you to be at all. The same equations that describe its silence also describe your breath. Both arise from the same woven continuum. Some scientists take this idea even further. They suggest that the entire universe might be the inside of a black hole, that the Big Bang itself was the moment when a collapsing region of another cosmos rebounded outward, its singularity birthing our own expansion. If true, then our reality is not outside anything. It is nested within the geometry of another. The multiverse becomes a forest of black holes, each universe blooming from the core of another, each horizon a seed of creation. Whether or not this is true, the metaphor holds a quiet grace. Reality is recursive. Each form gives rise to the next. Each curve births new curves. And every mystery, when followed far enough inward, leads to another opening outward. So when we say that matter might be a shadow cast by space-time, we are not reducing the universe to mathematics. We are discovering poetry within mathematics. We are realizing that the equations were not cold symbols, but a language written in the same rhythm that governs stars and dreams alike. The big idea about reality is not that we are insignificant. It's that we are integral. We are what space-time does when it wants to look at itself. Every thought is a fold, every heartbeat a ripple, every moment a continuation of the same cosmic pulse that hums through black holes and galaxies alike. The universe is not separate from us. It is us stretched across scales we can barely imagine. Our existence is not outside the equations of curvature, it is one of their solutions. And perhaps in that recognition, we find a strange kind of peace. To know that everything is connected through geometry is to see that nothing ever truly disappears. When a star collapses, its matter becomes curve. When a black hole evaporates, its curve becomes light. And when light spreads across space, it bends again, forming new patterns, new worlds, new minds to wonder. Reality is a conversation with itself, forever folding and unfolding like the slow breathing of an infinite being. And as we drift in that rhythm, we can feel the next turn approaching, where spinning black holes twist the surrounding space, dragging the very fabric of time into motion. A new layer of wonder waiting quietly in the curve's next spiral. The last thought still ripples quietly that everything, even matter itself, might be the shape space-time takes when it dreams of being seen. But dreams, too, can move. And when a black hole spins, the dream becomes a whirlpool. Black holes rarely sit still. They are born from stars that once rotated, and that spin is never lost. It condenses, concentrates, until the entire geometry turns with it. In such a place, rotation is not just a property of matter, it becomes a property of space. The result is something called frame dragging, a gentle phrase for an impossible effect. Space-time itself is twisted by the black hole's rotation. Imagine a spoon stirring honey. The honey moves not because the spoon touches every drop, but because the fluid transmits motion through itself. Now imagine that the honey is space-time thick and visible, and the spoon is a spinning black hole. Close enough to the center, and even you, an object that wants to stay still, would find yourself rotating. The fabric beneath you would not permit rest. This region where motion becomes mandatory is called the ergosphere. It exists just outside the event horizon like an atmospheric shell of swirling geometry. Inside it, space-time drags everything around the hole, and to remain still would require faster-than-light motion impossible even for light itself. So everything from photons to particles to entire magnetic fields is caught in the twist. Frame dragging blurs the meaning of direction. In normal space, you can face any way you choose. Near a spinning black hole, choice becomes illusion. The grid of space-time is rotating beneath you, its coordinates looping endlessly inward. The closer you drift, the more the universe insists you turn. There's a quiet wonder in that inevitability. Even geometry, which we imagine as fixed, can be set into motion. Space and time, usually the background, become fluid and alive, a slow vortex of reality itself. The first hints of this effect were glimpsed not in distant galaxies, but here, near Earth. In 2011, a satellite called Gravity Probe B measured how our planet's rotation twists nearby spacetime. The effect was tiny, only a few milliarc seconds per year, but it was real. Even Earth, gentle in its turning, drags the surrounding geometry slightly, as if space were a silk cloth caught between its spinning fingers. Now magnify that effect by millions by the mass and speed of a black hole, and you begin to sense the scale of cosmic motion. Frame dragging becomes more than a detail. It becomes an architecture, a sculpting of everything around the hole. Gas falling inward begins to swirl its motion, dictated not only by gravity but by twist. This is how accretion disks form those luminous rings we see in images of active galaxies. The dragging of space funnels energy into motion, compressing heat and light until they roar. From these disks, powerful jets can emerge, beams of charged particles, launched along the black hole's poles at nearly the speed of light. For years, their origin puzzled astronomers. But the secret, it seems, lies in frame dragging itself. The spinning hole, winds magnetic fields like taut strings, channeling energy outward through the surrounding plasma. The rotation of space becomes electricity, and electricity becomes light. It's strange to think that such precision emerges from such violence. Matter falling inward becomes radiant. Darkness births the brightest phenomena in the universe. Some of those jets extend for thousands of light years, tracing filaments through intergalactic space. They outshine entire galaxies, powered not by fusion or combustion, but by the twist of space-time alone. So, when we see those cosmic beams across telescopes, what we are really witnessing is space in motion, a gravitational gyre turning its own energy outward. The concept of frame dragging also redefines how we understand energy itself. In classical physics, you could think of energy as the capacity to do work. But near a spinning black hole, energy becomes orientation. Motion relative to the whole determines what positive or negative means. Inside the ergosphere, even the direction of time can seem to shift. One can, at least in theory, extract energy from this twist, a process first described by the mathematician Roger Penrose. He imagined a particle falling into the ergosphere and splitting into two. One fragment falls inward, its motion counter to the whole spin, while the other escapes, gaining more energy than the original particle had. The deficit is drawn from the black hole's rotation. Theoretically, a sufficiently advanced civilization could use this to draw power from a black hole, draining its spin slowly, like winding down a cosmic spring. It is a beautiful and eerie concept, energy harvested from geometry. Not from matter, not from fuel, but from the turning of reality itself. In that sense, frame dragging is both an engine and a metaphor. It shows that motion and structure are not separate, that the universe doesn't only contain energy, it is energy twisting and untwisting in endless equilibrium. The deeper you travel into this region, the stranger time becomes. Outside the ergosphere, you can still orbit. Inside, you are carried forward whether you wish it or not. The flow of space is irresistible. It's as though time itself has acquired spin, a momentum that pulls all futures into alignment with rotation. For a traveler falling in this would feel like being drawn into a cosmic whirlpool, each moment faster than the last, each second, both stretched and compressed. The stars above would smear into a single streak of light, their images bent by gravity and motion alike. Sound would not exist, but you could imagine the rhythm. A silent spiral, steady, endless. If somehow you could hover near that zone, not falling but not escaping, you would see light behave in dizzying ways. Photons emitted behind you might loop ahead, arriving from unexpected angles. You could theoretically see the back of your own head, reflected through curved paths of space. Every direction would be both inward and outward a kaleidoscope of geometry. This twisting, though born of rotation, has an emotional rhythm too. It reminds us that motion is not always linear, that the universe often turns back on itself, folding and reusing what it once discarded. Frame dragging is how space remembers that it can move. It's the universe practicing circular thought. And so from this perspective, black holes no longer seem static or final. They spin, breathe release, and exchange energy. They are storms in space-time. Not dead, but dynamic. their edges alive with rotation and radiation. They pull time into motion, yet also slow it, a paradox of speed and stillness intertwined. In the delicate balance of their spin lies a clue to larger questions: why galaxies align their rotations, why cosmic structures form filaments and spirals, why the universe prefers motion that curves rather than cuts. It seems that twist, not straightness, is the universe's natural language. Stars coil magnetic fields, planets spin galaxies, spiral, and even space itself, when touched by gravity, begins to swirl. Perhaps this is why we find circular patterns so calming, why orbits, waves, and cycles feel intuitive. We are echoes of a rotating cosmos, children of frame-dragged space. The geometry that turns around black holes also turns in us in the rotation of atoms, the beating of hearts, the rhythm of breath. As we drift outward from the ergosphere, the sense of rotation fades. Space settles again into its slow stillness. But the lesson remains: nothing in the universe is truly at rest. Even emptiness moves when mass turns within it. Even time can be bent into spirals. From the swirl of this gravity-born motion, new ideas emerge, light trapped in orbit energy, drawn from spin, and the razor-thin rings where photons dance forever at the brink. Another layer of mystery waits there between light and shadow, where even photons are caught in the geometry's embrace. The memory of motion remains. Even as we drift from the twisting ergosphere, the airless hum of rotation still lingers in thought. The feeling that space itself can be set spinning, that time can be caught in a slow, graceful spiral. Now we turn our gaze to what that spinning creates: the luminous architecture that forms just beyond the edge, where light and motion meet in an intricate dance. The photon ring, the ergosphere, and the strange, almost mischievous Penrose process a way, at least in theory, to steal energy from a black hole. Imagine being near a rotating black hole, close enough to feel the swirl of space beneath you. Light no longer moves freely here. Its paths curve bent by the geometry itself. Some beams spiral inward and vanish, while others, perfectly balanced, circle the whole in tight, eternal orbits. This delicate boundary, where light neither escapes nor falls, is called the photon sphere. It is a place of perfect compromise. Each photon travels around the black hole, bound not by mass, but by the curve of space. One misstep, one fraction of a degree too close or too far, and the orbit collapses, either plunging into darkness or escaping outward forever. It is the universe's finest edge, a razor between night and flight. The photon ring we see in images, that faint circular glow surrounding the black center, is built from countless near orbits like these. Each photon may have looped the black hole many times before finally finding a path toward our eyes. The light is distorted, stretched, and compressed by relativity. Its path curved so completely that what we see is not one perspective but many layered together. It's as if we're looking at the reflection of infinity folded again and again into a single loop. This ring is not only beautiful, it is revealing. Its shape and brightness tell us how fast the black hole spins, how space twists around it, and how gravity warps light itself. When astronomers captured the first image of the M87 black hole, the asymmetry in its ring was not an imperfection. It was a signature of motion. The bright side shows where light is moving toward us, boosted by the spin of the hole, while the dimmer side shows where it moves away, its energy stretched and faded. In that single image we saw both the stillness and the spin of the cosmos, a portrait of gravity in motion. Now step closer into the region, just outside the horizon, where frame dragging becomes irresistible, the ergosphere we touched upon before. Here, the twisting of space is no longer optional. Everything light-matter magnetism is carried around with the black hole's rotation. It is the most extreme example of how energy and geometry intertwine. The ergosphere has an odd shape, bulging outward at the equator, narrowing at the poles like a stretched sphere of distortion. Its outer boundary marks where space begins to drag, and its inner boundary touches the event horizon itself. Between them lies a zone of compelled motion, where the universe insists that everything must spin. Even light cannot resist. Photons traveling against the black hole's rotation are slowed, bent, their wavelengths stretched into long red sighs. Photons moving with the spin, however, are strengthened, their paths quickened by the same motion that once carved stars and disks and jets. Here direction defines energy. Movement becomes survival. It was within this rotating sea that physicist Roger Penrose imagined a daring trick, a way to extract energy from the spin itself. He reasoned that if you entered the ergosphere, you could take advantage of its twisted geometry. Inside the definition of negative energy becomes possible a property that exists nowhere else in the cosmos. A particle moving against the hole's rotation could, relative to distant observers, carry energy less than zero. If such a particle fell in, it would reduce the black hole's total spin. And if another particle escaped, it would leave with more energy than it began with. This is the Penrose process, a theoretical method of drawing power from the rotation of space-time itself. No mining, no fusion, no combustion, just the elegant borrowing of motion. It is as though the universe in its deep fairness allows even gravity's greatest hoarders to give something back. To picture it more simply, imagine throwing a ball into the ergosphere. If you aim it just right, the ball splits in two. One fragment is swallowed, the other returns moving faster than it left. The extra energy comes from the black hole's rotation. In this way, you could, at least in principle, slowly spin the black hole down, siphoning its rotational energy bit by bit. For something as vast as a black hole, this reservoir of energy is enormous. A single rapidly rotating black hole could, in theory, power civilizations for eons. It is the purest form of extraction imaginable, an energy source written into the geometry of the universe itself. But the Penrose process remains a dream. The conditions it requires are impossible for us to create or endure. The regions where it happens are too violent, too compressed in time and gravity. Still, the concept lives on in other forms, in the way astrophysicists understand how black holes can launch those immense relativistic jets. Magnetic fields twisted by frame dragging perform a similar trick, channeling rotational energy into luminous streams. So the Penrose process is not only a thought experiment, it is a mirror of reality playing out naturally in the hearts of galaxies. What fascinates most about this idea is how it erases the line between object and process. A spinning black hole is not just sitting in space, it is motion. Its energy, its structure, its influence all arise from rotation. To take energy from it is not to scoop matter from a thing, but to reshape the flow of geometry itself. The hole's spin in giving energy away also changes its own identity. It becomes calmer, slower, its shape adjusting toward symmetry. Even black holes can lose their momentum in the endless exchange of cosmic forces. Perhaps this is one of the universe's quiet rules that everything, no matter how extreme, must participate in balance. That even the strongest gravity must yield eventually to the slow diffusion of energy back into space. The photon sphere, the ergosphere, the Penrose process, each shows a different facet of the same truth, that gravity is not only pull but motion sculpted into form. Each layer closer to a black hole reveals not more chaos, but more structure. The closer you look, the more order you find. Even the photon ring, that fragile necklace of light around darkness, exists because the universe obeys perfect geometry. No randomness, no rebellion. Only the calm logic of curvature. And yet, in that calmness, something deeply human stirs. We are drawn to these patterns because they echo the way we move through time, circling, repeating, returning. We orbit our own experiences the way light orbits a black hole, sometimes escaping, sometimes falling back in. The photon ring is not just a cosmic artifact, it's a reflection of rhythm itself. As we drift further outward now, we carry the sense of motion with us. The black hole still turns behind us, its spin invisible but unending, its light bending paths across the universe. And in that faint golden ring, we remember that even light can be caught by gravity, and even gravity can give back light. Beyond this lies another truth, that falling into such a hole is far from simple. For matter, the path inward is not straight. It spins, collides, and resists heating until it glows brighter than whole galaxies. Before matter disappears, it performs its final dance of fiery, spiraling surrender. The light still circles behind us, a memory of motion, the photon ring glimmering at the edge of darkness, each beam of light tracing a perfect perilous orbit. But now imagine matter instead of light, dust gas fragments of a star drawn too close. How do they fall? How does something cross the final miles into silence? At first glance, falling into a black hole seems simple. Gravity pulls and matter moves inward. But the truth is far more intricate because the universe rarely allows a straight descent. Everything that forms stars or planets or clouds carries angular momentum, a measure of spin of motion around a center. And angular momentum resists change. The faster you fall inward, the more tightly you must turn. It is a law as gentle as it is relentless. You cannot fall straight when space itself demands a spiral. So, as matter draws near the black hole, its path curves, its rotation quickens. The closer it comes, the faster it must move until it approaches the ultimate limit, the speed of light. But nothing with mass can reach that speed. The universe forbids it, and so matter piles up just outside the horizon, caught between gravity's pull and the impossible pace of motion. This piling up forms one of the most radiant structures in existence. The accretion disk, a glowing whirlpool of gas and dust heated by friction, compression, and collision. Atoms in the disk rub against each other, their paths tangled by magnetism and turbulence. Each collision releases heat, and that heat becomes light. What we see across millions of light years as quasars or X-ray binaries is the light of falling matter resisting its fall. In that resistance, beauty emerges. A black hole, which should be perfectly dark, is often surrounded by brilliance. The disk around it can outshine every star in its host galaxy. It is paradox written in radiance, a beacon formed by the struggle against silence. If you could hover safely near the disk, the sight would be breathtaking. The inner edge would glow blindingly white, while the outer regions shimmered gold and amber. Each layer would whirl at its own speed, the inner ones racing close to light speed, the outer ones turning more gently, like slow tides circling a whirlpool. And all of it would drift slowly inward. But even hovering here is impossible. The radiation alone would vaporize anything solid. The magnetic fields are immense, rising and twisting through the disk like luminous vines. They can tear gas into jets, straightening the chaos into perfect beams that shoot outward for thousands of light years. These relativistic jets are among the most powerful phenomena in the cosmos. They pierce the darkness like lances of creation, illuminating the galaxies they escape from. And yet, their energy does not come from the black hole's interior. It comes from the disk itself, from the heat of resistance, from the spin and turbulence of matter caught in its final orbit. The black hole is not the source of light, but the reason light is released. Its gravity provides the tension that creates the flame. Closer still, there is a limit to how tight an orbit can be. At a certain radius, the centrifugal push from motion and the gravitational pull inward can no longer balance. This is called the innermost stable circular orbit, a quiet phrase for the edge of dynamical safety. Inside that boundary, no path loops forever. Matter either plunges inward, surrendering to gravity, or is flung outward by magnetic force. It is a threshold of inevitability, the line between orbit and fall. For a spinning black hole, this boundary shifts. Rotation pulls space itself into cooperation, allowing orbits to exist closer in on the side that spins with the hole and pushing them farther out on the side that spins against it. The result is asymmetry, a living asymmetry that shapes how the disk glows, how jets form, how galaxies evolve around their central hearts. Even geometry has a direction. Even gravity remembers the difference between left and right. From afar, accretion looks serene, a glowing ring slowly turning like a cosmic lantern suspended in blackness. But inside that glow, conditions are beyond imagining. Temperatures soar into the millions of degrees. Atoms are stripped into plasma electrons and protons flying freely in turbulent seas of magnetism. The friction converts motion into heat and the heat into X-rays, gamma rays, radiation beyond vision. If we could see the full spectrum, black holes would not appear black at all. They would blaze like miniature suns, their halos trembling with light, invisible to our eyes. And yet, through it all, the black hole remains unmoved. No matter how bright the disk becomes, no matter how much energy it releases, the horizon stays silent. Matter crosses that invisible threshold, and the light it once carried fades from view. From the outside, it seems to freeze and dim, never quite vanishing, never quite falling. Time itself holds its breath at the border. This illusion of stillness, so haunting and serene, is the result of relativity. From our perspective, the fall stretches toward eternity. From the matter's own perspective, the journey ends in an instant. Two truths coexisting, each complete, each unaware of the other's rhythm. Sometimes, as matter falls, it organizes itself in ways that seem almost intentional. Magnetic fields thread through the plasma, guiding charged particles along invisible lines. These structures create order within chaos, turning turbulence into symmetry. Through these filaments, energy escapes upward in jets, releasing some of what gravity draws in. It is an exchange, a kind of breathing infall and outflow, collapse and release. Astronomers see this pattern everywhere in young galaxies, where black holes grow rapidly in older systems, where jets fade and disks cool. The rhythm changes, but the structure remains. Even destruction, it seems, has a steady beat. The difficulty of falling into a black hole is not resistance in the ordinary sense. It is the dance between motion and law. Gravity invites, but rotation complicates. Energy must be conserved. Momentum must be balanced. And the universe, precise in its bookkeeping, never allows shortcuts. To fall inward is to satisfy 1,000 equations at once, to surrender to a geometry that demands perfection. If matter could somehow drop straight in without spin, without light, without friction, a black hole would be dark indeed. But nature seldom moves in straight lines. It curves, it spirals. It balances each motion with its opposite. The luminous disk, the jets, the photon rings, all of these are expressions of the universe's refusal to let things fall simply. And in that refusal lies all the beauty we see. The resistance creates radiance. The delay creates time. Even in collapse, the cosmos finds a way to shine. Somewhere right now, a star is straying too close to the black hole at the heart of a distant galaxy. Its outer layers are being drawn away, threaded into a glowing stream that wraps around the dark center. The core trembles, its light rising to a final brilliance before it's swallowed whole. Telescopes on Earth, decades or centuries from now, will catch that flash, a silent signal from a dying star falling into geometry's embrace. For the star, the fall is swift. For us, it is timeless. The light we see will travel through centuries, perhaps millennia, before it fades into the background hum of the cosmos. That is why falling in is hard, because the universe does not end easily. Every fall is stretched across time, translated into light, made visible before it disappears. And as that light crosses the universe, we too become part of the story, witnesses to the struggle between motion and stillness, gravity and fire, darkness and glow. The black hole does not devour thoughtlessly. It transforms it, recycles it, radiates. What we call destruction is only another way the cosmos keeps energy in motion. And so, from this threshold, from the glowing rim of the accretion disk, where matter burns in its final orbit, we can feel the next questions stirring. How many kinds of these cosmic hearts exist? Why do some blaze like quasars, while others remain almost silent? How does our own galaxy's black hole fit within that grand family of scales? Let us drift outward toward the realm of comparison, where black holes differ in size, in age, in brightness, and where our way of seeing them depends on distance, light, and time. The image still lingers in the mind, that glowing ring of light circling darkness, the accretion disk burning in its final dance. But not every black hole glows like that. Not everyone is surrounded by brilliance or jets or radiant spirals. Some wait quietly invisible even to the most sensitive eyes. They exist across an astonishing range of scales, from the tiniest tremors of gravity to the titanic anchors at the centers of galaxies. Each size tells a different story. Each reflects a different chapter in the life of the cosmos. And yet we mostly see the loudest, brightest ones, because light, as always, decides what we can know. Black holes come in families classified by mass, by origin, by the company they keep. At one end of the spectrum lie the smallest primordial black holes, tiny relics from the earliest moments after the Big Bang. They would have formed not from stars, but from density ripples in the newborn universe, places where gravity briefly triumphed before expansion pulled everything apart. These black holes, if they exist, might weigh as little as a mountain or as much as a planet. They would be ancient billions of years old, their horizons smaller than atoms of dust. No telescope has ever confirmed them. They may have long since evaporated through Hawking, radiation fading into faint warmth that merged with the cosmic background. But some scientists wonder if a few might still wander the galaxy dark pebbles of space-time, drifting unseen through the void. If one were to pass through our solar system, we might never know. It would bend light, subtly curve paths imperceptibly, and continue on a relic of the universe's first heartbeat. The next step up are stellar mass black holes, the kind born from the deaths of massive stars. They weigh between a few and a few dozen suns, and they are the most common kind we can imagine. Each one marks the end of a star's long, burning life, a quiet tombstone carved in gravity. Many of them reside in binary systems, orbiting a surviving companion star. When the living star loses material, its gas is drawn toward the black hole, forming a small, hot accretion disk that emits X-rays. These systems flicker and hum, the cosmic equivalent of campfires in the dark. Cygnus X1 was the first, but many others have joined its chorus since a population scattered through our galaxy, some quiet, some bright, some hidden completely until an outburst reveals them. If we could see them all at once, the Milky Way would shimmer with invisible heat. There may be millions of these small black holes drifting unannounced between the stars, each one carrying the memory of a sun that once was. Above them, vast in comparison, stand the intermediate mass black holes, the bridge between stellar and supermassive. For decades, they were ghosts of theory, neither small enough to form from single stars nor large enough to sit at galactic centers. But recent observations from colliding star clusters from gravitational waves detected by LIGO and Virgo suggest that they do exist. Perhaps they form when several smaller black holes merge their gravity, uniting into something new. Perhaps they are the seeds that grow into the supermassive giants at galactic hearts. These intermediate ones are elusive. They emit little light, and they live in quiet places, dense star clusters, ancient dwarf galaxies, regions of stillness between great structures. They may be the middle children of cosmic evolution, too shy to draw attention, too rare to count easily, but crucial to the story of how galaxies form and grow. And then there are the true monarchs of gravity, the supermassive black holes, millions or billions of times the mass of the sun. They sit at the centers of galaxies, like invisible hearts, their presence revealed not by light, but by the way stars and gas move around them. Every great spiral, every elliptical cluster of suns appears to revolve around one. The one in our own galaxy, Sagittarius A, is calm by cosmic standards. It sleeps at the center of the Milky Way, occasionally stirring when a gas cloud drifts too near. But others, like the one in galaxy M87, or the quasars seen in the early universe, blaze with unimaginable power. Their accretion disks and jets release energy that outshines trillions of stars combined. We see them across billions of light years, tiny points of light marking galaxies still young and forming. They are called quasars, and they serve as beacons to the dawn of time. Why do we see the largest black holes so easily when the universe must contain countless smaller ones? The answer lies in observation bias, a quiet distortion woven into how we perceive the cosmos. Light weakens with distance. Brightness fades with time. Only the loudest signals travel far enough to reach us. A small black hole feeding gently on a companion star is invisible beyond its immediate neighborhood. But a supermassive black hole feasting on torrents of gas and dust in a young galaxy blazes like a lighthouse, its light crossing billions of years to reach our eyes. So when we look deep into space, we are also looking deep into the past, an era when the universe was denser, when gas was plentiful, and black holes fed hungrily. The quasars we see from the early cosmos are not evidence that the universe was full of monsters. They are simply the ones bright enough to speak across time. In reality, many black holes today are quiet. Their disks thinned, their surroundings empty. Galaxies have matured, their fuel spent, their central engines gone to sleep. We live in a calmer epoch when even the great ones rest. This, too, is a lesson in perspective. The cosmos we perceive is shaped by what it chooses to show us. We see the fireworks, not the stillness, the youth, not the long twilight that follows. Most black holes are invisible, not because they lack beauty, but because beauty here is quiet, and our instruments still listen mostly for the loud. Even the word black hole is misleading. They are not holes, not absences, but continuities, places where the universe folds inward, where light loses its name but not its story. The ones we detect are simply those whose stories shine brightly enough to be retold. The sizes we've mapped so far may not be the only ones that exist. Some theories hint at ultramassive black holes, tens of billions of solar masses beyond even the largest known. Others propose micro-black holes that might form from high-energy events, tiny and short-lived. Perhaps nature builds black holes at every possible scale from subatomic to galactic, each following the same simple geometry. It would make sense for the laws that govern gravity do not change with size. Whether in the collapse of a star or the assembly of a galaxy, the equations hum the same melody. The only difference is tempo fast for the small, slow for the immense. Even time's rhythm shifts with mass. A particle-sized black hole might evaporate in a fraction of a second, while a supermassive one could outlast the universe itself. Scale, then, is the universe's most subtle art, using the same brushstroke to paint the infinite and the infinitesimal. And as we drift in this awareness, it becomes clear that the cosmos we see is not an even map, but a portrait painted by light and distance. we see what survived the journey. We see what was once bright, not what simply is. Every photon that reaches us has crossed time like an ancient traveler carrying a message from an era long gone. The farthest quasars we observe are images of youth, the universe's first experiments in gravity and flame. The smaller, quieter black holes of our own galaxy live in the present unseen, but near their silence folded into the night. So when you look up at the sky tonight, at the faint glitter of stars, at the deep dark between them, remember that even absence is uneven. What you see is not the full story, but a sampling of time's brightest echoes. The universe is vast, but it shows us only what remains visible, and that visibility depends on hunger, on heat, on light's willingness to travel. The greatest black holes draw our gaze, not because they are special, but because they are loud. The rest wait in stillness, hidden in the quiet fabric of the galaxy. Their gravity shaping the motion of stars, without ever revealing their form. It's a humbling thought. The universe we know is just the part of itself it allows us to see. And yet, even beyond these visible giants, the equations hint at stranger possibilities, at entities that might do the opposite of black holes pouring energy outward instead of swallowing it. Mathematics permits such cousins to exist: white holes, wormholes, bridges through the fabric of reality itself. Whether they truly exist or remain elegant abstractions, they extend the same geometry into the realm of imagination. From the silence of unseen black holes, from their calm gravity and quiet invisibility, the imagination of physicists began to wander outward again, to ask whether nature might ever create the opposite of such darkness. If a black hole is a place where nothing escapes, could there exist a place where nothing can enter? A mirror image of collapse, an outflow instead of an inflow, a phenomenon born not of hunger, but of release. That idea became known as the white hole. It began not as speculation, but as mathematics. Einstein's equations are time-symmetric. They do not favor one direction over another. If the equations allow something that collapses inward forever, then, by reversing time in those same equations, one finds a structure that expands outward forever. A white hole is the theoretical reflection of a black hole, where a black hole's horizon permits nothing to escape. A white hole's horizon permits nothing to enter. In such a place, everything flows outward. Light, matter, radiation, but never in. It is the universe's exhalation, a fountain instead of a whirlpool. No one has ever seen one. There is no observational evidence, no flicker of data hinting that white holes truly exist. But in the logic of relativity, they are permitted. And permission in the universe often means possibility. To imagine a white hole is to imagine the other half of balance. Black holes consume. White holes release. Black holes erase direction. White holes define it. They are mathematical twins forever separated by the arrow of time. Some theories suggest that every black hole could be connected to a white hole through a hidden tunnel in space-time, a wormhole, a passage through the folded geometry of the universe. If the fabric of reality can bend enough to collapse into a black hole, perhaps it can also bend enough to form a bridge. One side would swallow, the other would exhale. Matter falling into a black hole in one region of space could in theory emerge from a white hole in another, or even in another universe altogether. It's an idea at once elegant and unsettling that the universe could be connected to itself through tunnels invisible to any straight-line traveler. The mathematics for such bridges exists. They are called Einstein-Rosen bridges, named after the two physicists who first explored them in 1935. In their simplest form, they describe two sheets of space-time joined at a narrow throat, like two surfaces meeting at the tip of a tunnel. On paper, they connect black holes and white holes perfectly. In practice, they are unstable. The moment any matter or even light tries to pass through the bridge collapses. Gravity's precision is ruthless. The tunnel pinches shut before information can cross. Later work by John Wheeler, Kip Thorne, and others expanded the concept into what we now call wormholes. They asked a new question. Could such bridges exist stably? Could the universe, under the right conditions, hold open a tunnel between distant regions of space or time? The answer depends on a substance that might not exist at all. Exotic matter, something with negative energy, density able to resist collapse by pushing space outward instead of pulling it in. If such matter exists, it could theoretically prop open a wormhole's throat, turning a fleeting mathematical structure into a traversable passage. In science fiction, wormholes have become doorways, shortcuts across galaxies, gateways through time. In physics, they remain cautious maybes. Their equations whisper promises that reality has not yet kept. To build one, we would need to manipulate space-time on scales so far beyond our technology that even imagining the experiment feels like dreaming underwater. And yet the concept persists not because we can build them, but because they show us what the equations are capable of imagining. Black holes remind us of what happens when geometry collapses inward. Wormholes show us what happens when geometry connects. Both are lessons in curvature, in the way gravity translates energy into shape. In both cases, we are not speaking of tunnels carved through space, but of space itself rearranging. To travel through a wormhole is not to move through the universe, but to let the universe fold around you. Two distant points become neighbors. Two moments in time share the same breath. The mathematics allows it. Reality so far has not obliged. But perhaps, as with black holes before, what begins as abstraction may one day reveal itself in observation. After all, Einstein's black holes were once mere curiosities too, and now we have photographed their shadows. There is another way to see these concepts not as machines or shortcuts, but as metaphors for connection. In a universe that seems cold and separate, the idea of bridges of unseen links between distant places feels deeply human. Wormholes express a quiet longing for continuity across distance and time. They remind us that the cosmos is one continuous surface folded but unbroken, and that every point touches every other in the deeper geometry beneath appearance. Even if we never travel through one, the idea invites us to think differently about separation. Perhaps distance is an illusion of perspective. Perhaps everything is already entangled through gravity, through quantum fields, through the shared history of the Big Bang. A wormhole is not a violation of connection. It is the natural extension of it. There are deeper possibilities, too, where these mathematical bridges intertwine with the life cycle of black holes themselves. In some versions of quantum gravity, a black hole may not end in a singularity at all, but in a rebirth, a transformation into a white hole as it radiates the information it once absorbed. The collapse becomes a bounce. The inward fall becomes an outward expansion. In that view, the universe itself could be the interior of such a bounce, a cosmic rebirth emerging from the death of a black hole in some larger, older cosmos beyond our perception. It is a speculative idea, but a gentle one. It replaces finality with continuity, ends with transformations. The same pattern we see in stars, in atoms, in galaxies reappears at the largest scale imaginable, that nothing is ever truly lost, only changed in form and direction. When we think of wormholes, we often picture tunnels of light rings swirling with color gateways to elsewhere. But the truer beauty lies in the idea that the universe is not linear, not confined to the surface we see. Every point in space contains more connections than can be drawn in 3 dimensions. We live in a cosmos that folds and unfolds constantly, its geometry richer than intuition allows. Wormholes and white holes are like sketches of what space-time might do when it explores its own flexibility. They are the thought experiments of existence, geometry dreaming of self-recursion. Even if they never take physical form, they serve a purpose. They remind us that the known universe is not the limit of possibility. They remind us that the laws we've measured may only be local approximations of something grander, subtler, and perhaps more interconnected than we can yet see. So we let the equations breathe. We let the imagination wander. Maybe every black hole hides a seed of its opposite inside a core of release, waiting for some far future, when the collapse reverses, when the universe's long exhale begins. Maybe each white hole, if they exist, is the ghost of some forgotten collapse in a parallel cosmos. Maybe our own Big Bang was one such exhalation, a black hole's memory opening into a new sky. Whatever the truth, these ideas form part of the same rhythm we've followed since the first star's death, the rhythm of balance. Inward and outward. Collapse and expansion. Darkness and illumination. The cosmos never stops breathing, and we within it are caught in the same breath. And yet, for all their symmetry, the perfect white holes and wormholes of theory remain idealizations. Nature as it behaves in stars and galaxies is rarely so smooth. Real collapses are messy, irregular, imperfect. And the mathematics that describes perfect symmetry may fail when confronted with chaos. Perhaps the next turn in our journey is to see how the real universe compares to the elegant one on paper, to understand how the actual uneven birth of a black hole differs from the pristine shapes drawn in theory. For reality is never ideal. It wavers, fractures, breathes, and even in the heart of gravity, imperfection may tell a truer story. The ideas of white holes and wormholes linger like echoes, elegant in theory, perfect in symmetry, flawless in their balance of in and out, as though the universe had been drawn with a compass by a steady and patient hand. But when we turn from the blackboard to the stars, we find that the cosmos is not perfectly drawn. It is sculpted instead by turbulence, by temperature, by imperfection. The equations that predict eternity meet the matter that burns, and between them lies the messy truth of real existence. Black holes, as nature makes them, are not smooth and ideal like the ones in Einstein's papers. They are born in violence, in the irregular collapse of stars, in the fusion of galaxies, in the collisions of neutron cores that once shone with light. Their births are asymmetrical. their edges chaotic, their surroundings full of storms. A black hole begins not as a calm curve in space-time, but as a catastrophe. A star dies unevenly, its magnetic fields twist. Its explosion sends waves of light, matter, and radiation in all directions. The collapse does not follow clean geometry. It ripples, shudders, and folds. Only after the chaos settles does the horizon find its symmetry. Even then, the whole is not isolated. It sits within a sea of debris surrounded by matter still struggling to decide its fate. Gas clouds fall inward. Some orbit, some escape. The magnetic fields are tangled and alive, feeding the surrounding disk with energy. Jets burst outward, not in perfect alignment, but in wandering beams, their directions changing with time. Everything moves, shifts, and self-corrects. In theory, a black hole can be described by just 3 numbers: mass, spin, and charge. In reality, its story is written in countless variables: the rotation of the parent star, the density of nearby gas, the history of its collisions. Each one slightly distorts the pure solution, adds a wrinkle to the curvature, a deviation from perfection. The result is still a black hole, but one that bears the fingerprints of its birth. Even the event horizon, which we imagine as perfectly smooth, may in reality flutter and flicker. Quantum effects. Magnetic waves and accretion turbulence may ripple across its surface, turning it into something more dynamic than static. Like the surface of the sea, it appears calm from afar, but up close it is alive with motion. The same imperfection shapes the way we see them. Our telescopes capture not timeless stillness, but snapshots of moving systems. The light we observe is distorted not just by relativity, but by dust plasma and the shifting glare of interstellar gas. Every image of a black hole, every data point in a radio map is filtered through noise. Scientists spend months removing the static, reconstructing what the cosmos truly sent us. Even the famous portrait of M87's shadow was not a photograph in the ordinary sense, but a patient reconstruction of waves, the universe's message assembled piece by piece, like an echo turned back into sound. That's the irony of physics at its extremes. The purer the equations, the rougher their expression in nature. Perfect spheres give way to swirling disks. Clean curves meet turbulence. In the same way that language cannot capture silence, math cannot fully capture chaos. And yet, those imperfections are not failures. They are how the universe breathes. Without them, there would be no stars, no planets, no structure at all. Symmetry alone is lifeless. It is the breaking of symmetry, the small imbalances in spin and density and heat that allows matter to gather, that lets galaxies grow. Even in collapse, disorder is the seed of form. Physicists often say that the singularity inside a black hole marks the breakdown of the known laws of physics. The equations of general relativity predict infinite density, infinite curvature, a point where time and space lose their meaning. But infinity is not a physical thing. It is a sign that our model has reached its limit. In truth, nature likely hides its singularities behind deeper structures we cannot yet see. Quantum effects may smear out the infinite, replacing the point with a region of extreme but finite density. Loop quantum gravity string theory and other attempts at unification all hint that reality becomes discrete at small scales, made not of continuous fabric but of tiny loops, tiny quanta of geometry. If that is true, then the singularity is not an end, but a doorway to something new. These corrections remind us that mathematics is a kind of idealized poetry, beautiful, concise, but always written in approximation. It tells us what would happen in a universe of absolute symmetry and infinite precision. But the real universe hums with asymmetry, with imperfection, and that imperfection is what makes it visible. Even time itself may behave differently in the real black holes of the cosmos than in the equations we draw. In theory, the horizon is sharp, once crossed, no return. But quantum uncertainty blurs all boundaries. Particles and radiation may leak across the edge, their probabilities spread across space and time. Some researchers propose that horizons are not fixed surfaces but fluctuating membranes, fuzzy regions of information exchange that pulse with activity rather than silence. Perhaps this is what Hawking radiation truly means. Not that black holes are leaking in isolation, but that they are communicating their horizons alive with quantum conversation. The perfect stillness of mathematics gives way to the living restlessness of reality. It is comforting in a quiet way to know that even black holes, symbols of absolute gravity and control, are shaped by imperfection. They are not perfect voids. They are evolving, shifting entities in an evolving, shifting cosmos. Some grow by feeding on stars. Some merge with others. Some evaporate slowly into light. They age. They change. They leave traces of their passage, ripples in space-time, jets of plasma, waves of radiation. Even they are part of time's unfolding. When two black holes merge, the moment of collision is not smooth. The horizons distort, stretching into elongated shapes, their edges rippling like merging drops of water. Space itself quivers with gravitational waves, carrying away the imperfections as music. In the end, the new black hole settles spherical once again, but only after singing its brief gravitational song. The universe, it seems, loves imperfection enough to make art from it. So when we compare real black holes to their ideal mathematical forms, we're really comparing experience to imagination. The equations describe what the universe intends. Reality shows us what it becomes. Between the two lies a conversation, a constant negotiation between law and chaos. Without one, the other has no meaning. This dialogue continues at every scale. The same interplay shapes the atoms in your body, the weather on your planet, the spirals of galaxies. Mathematics dreams of purity. Nature responds with variation. And it is within that variation, the gap between expectation and manifestation, that beauty resides. Even our best theories, the ones we call complete, are sketches drawn against the infinite. Einstein's equations hold steady until we reach the singularity. Quantum mechanics holds steady until gravity joins the conversation. Somewhere in the heart of a black hole, those frameworks overlap, and neither knows how to speak clearly anymore. There, in that uncertainty, is where new physics waits. Perhaps, when we finally understand it, we will find that imperfection itself was the missing symmetry all along, that reality's irregularities are not errors to be corrected, but features of a deeper order, too subtle for perfect equations to describe. And so the ideal and the real coexist, theory and turbulence entwined. The black holes we study are both symbols and beings born of math and of matter. They are what happens when perfection collapses and becomes dynamic again. From here, our path bends toward the final arc, the question of what comes next for these beings of gravity. Do they end? Do they fade into radiation or rebound into something new? Does information die, or does it transform? Our journey turns now toward the final phase of the black hole's life, toward ideas of loop, quantum gravity, white hole rebirth, and the quiet possibility that creation might emerge from collapse. From the meeting of the ideal and the real, we drift gently onward beyond the mathematics that falters at infinity, toward the possibility that even in collapse the universe finds renewal. The black hole, once imagined as an end, begins to resemble a process, a chapter in a longer continuous book of transformation. The thought hums quietly through physics. Now, perhaps, nothing in nature truly dies, not even a singularity. Perhaps every fall is also a beginning. To understand this, we trace the imagined life of a black hole from its birth in a star's final collapse to its long aging in darkness, to its fading through quantum release. When a massive star exhausts its fuel, its inner core, once supported by fusion, surrenders to gravity. The outer layers rebound in a supernova, an outburst bright enough to outshine an entire galaxy for a moment. But the core continues inward, compressing beyond the strength of atoms, beyond the resistance of neutrons, until nothing remains to oppose the pull. A black hole is born in that silence, a new curvature sealed from the outside world. In its youth, it feeds greedily. Nearby gas dust and even companion stars fall into orbit, forming a disk of fire. Its spin tightens, its mass swells. It glows indirectly, not by its own light, but by the energy released from what it consumes. Over millions of years, its surroundings thin, its appetite slows. The feeding ends and it becomes quiescent, invisible except for the gravity that guides nearby stars. But even in this long sleep, a black hole is not truly silent. According to Stephen Hawking's remarkable insight, space, near its horizon, is not empty. It trembles with quantum fluctuations, pairs of virtual particles that appear and vanish faster than any eye could see. Normally, these pairs annihilate their brief existence, canceling out. But at the edge of a black hole, the balance breaks. One particle falls inward, the other escapes outward as faint heat. Over immense time, this Hawking radiation slowly drains energy from the black hole. It glows not with visible light, but with a whisper of thermal breath, colder than cosmic background, yet persistent. The black hole, once the symbol of eternal hunger, becomes a candle that eventually burns itself away. The smaller the black hole, the faster this evaporation proceeds. A stellar mass black hole would take far longer than the age of the universe to fade. But if there are tiny primordial black holes, some might be completing their lives now, releasing final flashes of radiation that ripple faintly through the cosmic sea. It is a strange inversion. The densest objects in nature end not in implosion, but in disappearance. Even gravity has a lifespan. Yet this fading raises a profound question, the information paradox. If matter and light fall into a black hole, their details seem to vanish behind the horizon. And if the black hole eventually evaporates, what happens to that information quantum mechanics insists that information can never be destroyed. It can be changed, scattered, hidden, but never erased. Relativity, meanwhile, appears unconcerned with such bookkeeping. The two great pillars of modern physics seem to disagree at the edge of a black hole. Reconciling them has become one of science's quiet obsessions, and in that search, new ideas have emerged, among them the framework known as loop quantum gravity. Loop quantum gravity, or LQG, proposes that space-time itself is not infinitely divisible, but made of tiny discrete loops, quanta, of geometry woven together like threads in an invisible fabric. Where relativity treats space as smooth LQG, imagines it as granular. Each loop defines an atom of volume, a smallest possible unit of curvature. Just as matter is made of particles, space might be made of loops. At ordinary scales, these loops blend into the seamless flow we perceive. But near a singularity, where curvature grows extreme, the granularity becomes visible to the laws of nature. It stops the infinite compression predicted by relativity. Instead of a singular point, there is a region of maximum density, a quantum pressure that resists further collapse. And then, perhaps, something remarkable happens. The collapse rebounds. In this view, the heart of a black hole is not a terminal pit, but a bounce point, a moment when space-time, compressed beyond limit, pushes outward again. The black hole may, in its final whisper, transform into a white hole, the mirror opposite of its birth. Instead of swallowing matter, it releases it slowly, not as chaos, but as information restored. The transition would be gentle spread over vast cosmic timescales. The black hole would shrink until quantum effects could no longer be ignored. Then, at the smallest scale, it would release the memory it had stored not as perfect recreation, but as harmony, as energy returned to balance. In this way, the universe might keep its books perfectly after all. Some theorists have extended this idea even further. If a black hole can bounce, then perhaps the Big Bang itself was the rebound of a previous collapse. An entire universe contracting under gravity, compressing into a single dense state, then reversing, expanding anew. The cycles could be infinite, each universe born from the remnants of the last, each Big Bang, the white hole moment of a dying cosmos. It is an audacious picture, cosmic reincarnation played out across eons. But it carries a quiet poetry. Nothing wasted, nothing final. Only change curvature, turning inward, then outward again. Even if the truth proves different, the thought itself is calming. It reminds us that endings and beginnings are not separate categories, but phases of the same rhythm. A black hole's evaporation might not be loss, but transformation, a continuation written in another language. The black hole's life cycle then might be seen as a vast arc of exchange birth and collapse growth through accretion rest, through dormancy, decay, through radiation, and rebirth through quantum release. Each phase speaks to a balance between order and entropy, between absorption and emission. Even the darkest phenomena participate in the cosmic conversation of energy. Imagine for a moment the very last moments of a small black hole's life. After eons of fading, its horizon shrinks to microscopic size. The radiation around it glows faintly blue-white, temperature rising as mass decreases. At the final instant, the black hole releases a burst of energy, a gentle sigh of all it once contained. From our perspective, it ends in light. From another, it might begin again. In these theories, loop quantum gravity becomes more than mathematics. It becomes philosophy written in geometry. It suggests that everything, even space and time themselves, has texture, that nothing is truly continuous, and that continuity is an illusion woven from infinitesimal parts. To exist is to be quantized, to be built from finite loops, finite moments, finite lights that never fully vanish. It also implies something quietly profound, that the universe remembers itself. That no curve of space, no flicker of energy is ever forgotten. It may transform, but its essence remains within the structure of reality. The cosmos, then, is its own archivist, and if the universe can remember, then perhaps we too are part of that memory. The atoms in our bodies have passed through the hearts of stars, perhaps through black holes, perhaps through the edges of ancient bounces. The light we see tonight carries information from before Earth existed. The breath we take contains molecules older than the sun. We are continuations, not creations, part of a story that folds and refolds forever. In this view, a black hole is not destruction. It is metamorphosis. It hides information only to release it later in new form. Its silence is not absence, but incubation. The same curvature that swallows light eventually gives it back, diffused into the wider glow of the cosmos. The equations are still uncertain, the models still debated, but the rhythm feels right. Nothing in nature simply ends. It shifts, it breathes, it evolves toward balance. And as we listen to that rhythm, birth, collapse, radiation, rebirth, we begin to sense the final truth of our journey, that black holes are not the universe's edge, but its mirror. They show us how everything transforms, how even gravity, the most certain of forces, learns to let go. From this understanding rises the final reflection, the takeaway that threads through all these mysteries. What black holes teach us is not despair, but humility. Not destruction, but continuity. They are reminders that our knowledge, like the cosmos itself, is unfinished, still expanding, still bending toward light. From the whisper of quantum loops and reborn light, we arrive softly at the edge of reflection. The long path through black holes, from collapse to curvature, from fire to silence, has revealed not finality, but continuity. Each stage, each paradox, each theory that hums between gravity and quantum thought has pointed us toward the same quiet truth, that the universe does not end. It transforms. The story of black holes is not about disappearance. It is about persistence, about how energy, form, and meaning move through change without loss. We began with the idea of darkness as an ending, and we found instead that darkness is a beginning in disguise. Perhaps this is the universe's oldest lesson, that even its deepest mysteries are invitations to see differently. When we look at a black hole, we are really looking into the structure of understanding itself. It challenges the things we think we know. What time is, what matter is, what real means. It reminds us that even our most confident concepts, space, duration, motion, are not fixed, but conditional, dependent on perspective and scale. Einstein once wrote that reality is merely an illusion, albeit a very persistent one. A black hole is the most persuasive proof of that idea. It bends not only the path of light, but the path of thought. Around it, our intuitions stretch and fail. Our vocabulary dissolves. We are left with metaphors, folds, bounces, bridges, ways of describing what cannot yet be fully seen. But within those metaphors lies something honest, a willingness to accept that the universe is more subtle than any equation can hold. For a moment, consider how this journey began. A massive star exhausted its strength, its light dimming into gravity's embrace. Out of that surrender came a new geometry, one that defied ordinary meaning. And from that geometry came new insight, new laws, new questions. Every fall has been followed by expansion. Every collapse has inspired imagination. Even our understanding behaves like a universe contracting into confusion, then expanding again into clarity. The takeaway is not only physical, it is existential. We too are participants in the universe's great balancing act. Our lives obey the same law of transformation. We rise, burn, change, fade, but we do not vanish. The atoms that carry our breath will one day drift into clouds, perhaps into new stars, perhaps into planets, yet unnamed. We are already part of eternity woven into the same field that curves around every black hole. Black holes reveal how intimately connected the infinite and the infinitesimal truly are. They are born from single stars, yet influence entire galaxies. They occupy points smaller than thought, yet shape structures larger than imagination. They show us that scale is an illusion of distance. The same equations that govern the collapse of a nucleus govern the rotation of a galaxy cluster. Physics is not a hierarchy. It is a harmony. And within that harmony, we find humility. Black holes remind us that knowledge itself is partial, that even the brightest minds must bow before mystery. Their paradoxes event horizons. Time dilation, information loss are not failures of understanding, but thresholds. At those edges, science becomes poetry again. Language reaches its limits, and what remains is awe. Even our tools for seeing have been transformed by them. To observe what cannot be seen, humanity learned to listen to gravity itself. The detection of gravitational waves turned the universe into a soundscape, ripples in the fabric of reality passing through us, like echoes of cosmic collisions. When two black holes merge, they do not only shake space, they sing. And we, with delicate instruments on Earth, can hear that distant choir. It is not metaphor, it is measurement. We have heard the voice of curvature, and it is gentle, low, and vast. Those waves tell us that even the most extreme events unfold according to rhythm and grace. No explosion, no chaos, only the slow fading of vibration into stillness. The cosmos does not end abruptly. It exhales. In their way, black holes are teachers of stillness. They show how energy can move without visible motion, how transformation can occur without noise or flame. They are patience made physical time stretched until it almost stops. They hold their lessons in silence, teaching through gravity what words cannot. Even their light, the radiant disks and jets that surround them, is not their own, but borrowed from what falls too close. They remind us that luminosity is often the product of surrender, that what yields can sometimes shine the brightest. If the universe has a moral, perhaps it is this, that to release, to curve, to accept gravity and time is not to lose, but to transform. Every theory we build around black holes, relativity, quantum mechanics, loop, gravity, all these languages of precision serves a single yearning to make sense of the unseen. We chase the edge of comprehension, knowing it will recede. And yet, the chase itself is the meaning. The pursuit is not to conquer mystery, but to be transformed by it. To study black holes is to practice humility. It is to acknowledge that we are small, but not insignificant tiny observers with minds capable of tracing the shapes of infinity. That is its own form of cosmic grace. We are part of the universe that tries to understand itself. Each question, each model, is the cosmos thinking out loud. Perhaps that is the ultimate unity. The knowing and the known are not separate. The stars study themselves through us. Their light becomes thought. Their collapse becomes curiosity. Their rebirth becomes wonder. When we finally step back and see all these ideas as one great continuum formation, evolution, evaporation, and beyond, we realize that black holes are not exotic anomalies. They are central to the way the universe keeps its balance. They regulate galaxies, shape the distribution of matter, and sculpt the light that travels between worlds. Without them, the cosmic dance would lose its rhythm. And so rather than thinking of them as destroyers, we might see them as caretakers, guardians of transformation, custodians of equilibrium. They gather, they compress, they release. They ensure that energy once concentrated will one day disperse again. They keep the cycle of creation honest. In their silence, they also remind us of how little we need to grasp to belong. You do not need to know every detail to be part of the cosmos. You already are. Your heartbeat, your thoughts, your stillness tonight, all of them are expressions of the same physics. The gravity that bends starlight holds you gently to the earth. The time that slows near horizons ticks softly within your pulse. You are not outside the laws of the universe. You are one of its solutions. When you look at the night sky, you are not looking out, you are looking in. The same geometry that folds around black holes folds within you. The atoms in your body have traveled through fire and collapse, through dust and radiation, through endless transmutations of matter and meaning. You are, in every sense, a continuation of the cosmos's long unfolding. And so, as we reach the quiet end of this exploration, the takeaway becomes simple. Black holes are not meant to make us despair. They are meant to awaken wonder. They show that mystery is not the opposite of knowledge, but its companion. They reveal that limits are not walls, but invitations to look deeper. And they remind us with the gravity of truth and the grace of silence that we belong to something vast, not outside us, but within us. The same curvature that bends galaxies bends thought. The same darkness that swallows light nurtures understanding. The same stillness that reigns in their depths waits quietly within the folds of our own minds. We are not separate from the night sky. We are its awareness. Even as you rest now, the universe continues its slow turning. Stars being born, black holes breathing in and out, light stretching across time. You need not hold the equations nor remember the theories. It is enough to know that everything moves toward balance, and that you are part of that movement. The cosmos is patient. It curves gently around itself, carrying all things energy, matter, thought in one unbroken conversation. You can rest in that truth. The universe continues vast and calm. The same light that escapes the edge of black holes crosses the darkness to reach your eyes. And even when your eyes close, it keeps traveling endlessly softly forever. If you are still awake, you may listen to another chapter. Otherwise, let the stars keep their quiet watch. Sleep well beneath the infinite.